In this video, 6.2 Other Cross-Sections, our objective is to generalize this slicing method to other solids. And actually, we're going to talk about the more general idea of taking slices in general and showing that certain volume formulas work. So let's actually start with an example where we know where we want to go. So we're going to be looking at the volume of a right circular cylinder. And remember that our we've seen this before. So the thing that we want to prove. So statement. The volume of a circular cylinder is pi r squared h, where we understand that r is the radius of the cylinder. I'm going to go ahead and draw in how we want to think about this cylinder. So here's the base, okay, that you can imagine is laying on this y-axis. So it's the y-axis is going through the base, through the diameter, and it's going to be, and the x-axis is completely perpendicular to that whole base. And so you know that a right circular cylinder is basically just the prism formed by taking that circle and extending it outward. So here's the radius. So that distance right there is the radius. And here's the height. So the height is really just how far into the x-axis, positive x-axis, the right cylinder extends. And so we can take two approaches here. One's going to be a little bit more complicated, but they should give us the same answer. So we'll call this the proof by approach 1. Our first approach, we're going to use the slicing method. So we're going to think of this as a solid of revolution. Slicing with a solid of revolution. And how is that? So if we think about this cylinder as being generated by taking this function, so this curve, bounded between, so the area bounded between this curve, the x-axis, and the left endpoints 0 and the right endpoint h. So take the region bounded by in this case, this function, it's flat, it's just r. So we're going to take y equals r, the x-axis, so y equals 0, x equals 0, and x equals h. And we're rotating that about the x-axis. And revolve about the x-axis. Then this means when we're taking our cross-section, so the slice that's going to be filled out is this infinitesimally thin disk here that's being generated by a rectangle of height r and width dx. In other words, the infinitesimal volume is going to be pi r squared dx, which isn't surprising. Now, that means our volume, when we integrate from 0 to h, pi r squared dx is going to be, oh, actually, I don't need the integral symbol anymore because I'm just going to go ahead and integrate. So pi r squared x from 0 to h. And if we plug in h, we will just get the actual volume. Plug in 0 and you get 0. So this is pretty clearly our answer. Okay, so this isn't too surprising because we actually kind of used the conclusion and the premise in that this is the definition of. We just said add up the tiny cylinders together and you get a big cylinder, which isn't hard to see a stretch of the imagination like that. On the other hand, we can do this by circular cross-section. Okay, so approach 2. So this is more akin to the more general approach that we had in the beginning, which is that we are thinking about volume as the integral from a to b of the area function of some cross-section, infinitesimally thin, times dx. Okay, but importantly, this cross-section is a circle of radius r. So to no surprise, that is going to be exactly the same picture, just instead of thinking about infinitesimally thin cylinders, we're going to whoosh away the detail about dx, and that's just going to be baked into the formula. So in other words, we're talking about the integral of pi r squared. And remember, it's constant, right? It doesn't depend on which value of x we're talking about. So we actually end up with the exact same integral, and in this case, we're just done, right? It's pi r squared h. So not terrible, not hard to see. Okay, let's see a more exciting example. Okay, so in this case, we're going to be talking about a right circular cone. Okay. So this is just what you would expect a cone to look like. The words right circular just mean it's not some funky general cone. So let me just draw it real quick then. So it should look something like this. The base is a circle with radius r. The height is h. And it's called right circular because when you take a peek inside the cone, you'll see that it's actually this triangle being rotated, this right triangle being rotated a full 2 pi, which actually suggests how we might be able to take, we might be able to do this integration pretty easily. But we're going to do this by cross-section, okay? So the idea here is that when we want to take cross-sections, how should those cross-sections look like? What exactly are we seeing here? And so if we imagine we start at the bottom, so we have this circle, then any circular cross-section like this, okay, is going to be some distance away from the base of that cone. So here's what we'll do, okay? We'll imagine that the axis going through this is the x-axis, which means we are looking at between 0 and h, okay? We want to find out our target is a of x being the circular cross-section. But this depends on x, right? All we have so far is r and h. Let's zoom in again on that triangle that makes up the middle of the cross-section. Assume that's a right triangle, sorry. Okay. So at some point x here, all right, we want to find out what this length y is. So that means, more accurately, let me write down x is this right here. Or we can say x is this smaller length, like this. Okay. So notice we get two similar triangles, one inside each other, one inside the other, I should say. This is r, and the whole thing is h. All of this is to say that by similarity, and this is a consequence of geometry, right? By similarity, the ratio r over h is the same as the ratio y over x, which suggests y equals r over h times x. Why do we need this? Well, y is the radius of the circular cross-section that I've highlighted here. In other words, if originally we had a of x equals pi y squared, well, now we've written it in terms of x alone. So pi r over h times x squared, which equals pi r squared over h squared times x squared. And now we can use the cross-section formula and just perform the integral. So we find the volume is the integral from 0 to h of pi r squared over h squared times x squared dx. Now everything before the x squared is a constant, so that's not going to be affected. That means we end up with pi r squared over h squared times x cubed over 3 from 0 to h. Okay, we're using FTC2. And then if you see here 0, that when you plug that in, that's going to give you 0. So we can just safely ignore that part. That means all we worry about now is this right here, which is some h's cancel, two pairs specifically, and you just end up with 1/3 pi r squared h, which you'll notice, and this is very, very fun, very interesting fact. You take a cone, so here's my cone again, of radius r and height h. Now you inscribe it inside a cylinder of the same height. So it's like you have a cylinder that has the same base, and it has the same height, right? So this is h again, this is r, then the volume of the cylinder is 3 times the volume of the cone. Very weird, isn't it? But it's true. Okay, so we have one last worthy example of our time. And this one is a standard one that I think is usually covered when we talk about things like this. And it doesn't really have a name, but let's come up with one. The thing to keep in mind about this is the solid we're talking about here is, so our task is to find the volume of the solid whose base is a disk of radius r, circle, right? And whose cross sections are squares. So let me draw this for you, because I think it's hard to appreciate what this thing must look like. I'm gonna try to make this as big of a drawing as possible. Okay, so here we have the y-axis, the x-axis, okay? And its base is a circle of radius r. Imagine that's a circle. I'm sorry. So radius r, so that means that's r there, that's r there, okay? And its cross sections are they are squares. So from here to here, right? That's a length, side length of 2r. That means the height there is also 2r. See if I can do this justice. So that's the cross section at that point, right? And then imagine at some other point here, right? So we have another line parallel to the y-axis. And then that length is, whatever it happens to be. Maybe it's 1, who knows. Then we stand up another square right here. So the height at those points is the same as twice the radius, well, not the radius, but twice the length there. And similarly on the other side, right? So, no, let's undo that. I want to make this as nice as possible, because to really appreciate what this thing looks like. Dang it, I did it again. To really appreciate what this thing looks like. Dang it. I am not getting the angle right. Hang on. That's better. It's not perfect, but that's better. Okay. So you should imagine then that it basically looks like this. Okay. So there's this. That's the shape of this thing. Super weird, right? All right. Okay. So, let's call it something. I'm going to call it the car solid, because it kind of looks like how cars look nowadays. It's the car solid. Okay. So the question is then, how do we find the volume of this thing, right? So it depends on what variable we want to work with. Do we want to work with x? Do we want to work with y? I think we should work with x, okay? So our integration is going to happen with respect to x, which means here we have x is between negative r and r. Now, we may not want to work directly like this. We may want to just look at just the positive side of the x-axis. And then remember that there's some symmetry going on, and so we're going to end up multiplying by 2. Right? That's up to us. But for now, let's just go with that, right? So from negative r to r. Then, with the thing that we're integrating is this cross-section. The question is, what is that? What is the area of that? Because we know it's a square, but what's the side length? All we know is that the side length is 2 times y, the y corresponding in x, along that, along the base. So in other words, I'm going to need another space here. We know, so remember we said s equals 2y, which is the side length of the cross-section that we're going to take. We also know that x squared plus y squared equals r squared. We're going to use that to our advantage because then we can use the observation that y depends on x, specifically using the square root of r squared minus x squared, right? Just some right triangle trig, basically, that we're doing here, okay? That means then a of x, which is, of course, 2y squared, because that's the side length squared. That means it's going to be 4y squared, which is the same as 4 square root of r squared minus x squared squared. That's 4 r squared minus x squared. And now that's just in terms of x. R is a constant. It's the constant for this car solid. And that means our volume calculation is going to be the integral from negative r to r of 4 r squared minus x squared dx. And there's some nice symmetry here that you might notice. For instance, even integrand, right? This is an even function. That means you can use the even integrand rule for what is it called? For integrals, sorry. And just perform the calculation 2 times the integral from 0 to r of that integrand, r squared minus x squared dx, which is what I was alluding to earlier, that you can exploit the symmetry of the solid to make this an easier calculation on you. And so we have 2 times 4 r squared minus 4 x cubed. Yeah, let me just draw this all over again because this doesn't look good. 4r squared x minus x cubed over 3 from 0 to r. If you plug in 0 in this case, it all is going to go away, so the only thing we care about here is the r. So we end up with 2 times 4r squared times r minus 2 times r cubed over 3. And if you notice, we get 2 terms that involve r cubed. I'm going to save you some of the arithmetic headache here, and you end up with 16r cubed over 3. And that's our answer. Okay, so in a future video, we're going to start talking about the method of cylindrical shells, which is a different technique for finding the volume of a solid of revolution. But keep in mind that a lot of what we're doing here is fundamentally all the same, right? We're still taking these infinitesimally thin whatevers and adding them all up. So, and if here are infinitesimally thin things that we were looking